Welcome to the deep dive. Today we took a stack of sources that honestly look less like pure math proofs and more like blueprints for some kind of intricate machine. We're talking spinning vectors, geometric ribbons, curvature, all aimed at, well, at cracking the Riemann hypothesis, RH. Our mission today is really about finding a shortcut. We're diving into a totally novel, kind of elementary geometric way to get at the deep structure of prime numbers. Forget wading through complex analysis for a moment. We're looking for, like, a geometric radio we can tune to hear the prime's secret music. And what does that radio tell us? Okay, let's unpack this. It's a big claim.
It really is. And what's fascinating is the core idea here. Usually, the rhythm of primes, how they cluster, spread out, oscillate, that's all tied up with the zeros of the zeta function.
Yeah.
Heavy stuff. This geometric framework says, nope, you can read those exact same spectral fingerprints, the same music, directly from simple finite Euclidean geometry.
Simple Euclidean geometry.
Well, there's a catch. You have to tune the instrument just right. And that tuning mechanism, the sources insist, is fundamentally tied to chirality, handedness.
Handedness. Okay.
Get the geometry right, ground it properly with this chirality, and suddenly you unlock these surprising, measurable consequences. For number theory, sure, but also for practical things like modern cryptography.
All right, let's start with the physical object itself. The sources call it the prime polygon Lune. It starts with something called a prime phasor walk. That sounds technical. Can you give us an analogy? How does this walk actually look?
Okay, imagine a giant, slightly wobbly wagon wheel spinning on an axle. For every prime number p you hit on the number line, you attach a little spinning vector, like a tiny force. All these little forces, these vectors, they add up. The wheel itself is always moving forward, but the sum of all those spinning parts makes the center of the wheel trace out a path. That's the walk.
Okay, a wobbly wagon wheel. And as it spins and moves forward, the path it sweeps out covers an area, the ribbon area, AMT.
Exactly. Now, that area grows pretty much linearly with time, T. But we don't really care about the steady growth.
We care about the wobble.
We care about the wobble, the deviation from the straight path. This geometric shape, the Lune, lets you isolate just that wobble. And the sources show that these wiggles, this wagon wheel wobble, encodes the exact same spectral frequencies you get from the Riemann zeta function zeros.
So the rhythm of the primes is literally in the wobble of this geometric shape. The sources mention three basic Euclidean facts, Q1 to Q3, to back this up. But here's the bit that really jumped out at me. They confirm the average size of these wobbles, the mean square size, falls at the RH rate. Why is that such a big deal?
Because the Riemann hypothesis, at its heart, is a statement about how controlled those prime wiggles are. It sets a strict limit on how big the oscillations can get. So finding that this simple physical geometry, just vector spinning, perfectly matches the RH prediction, well, it's like finding an ancient map made with sticks and stones that points to the exact same spot predicted by, advanced satellite imaging.
Wow. Oh.
It means the geometry isn't just mimicking, it's intrinsically linked to that deep analytic truth.
And they don't stop there. The sources detail two protocols showing this isn't just descriptive, it's predictive. Tell us about Protocol 2, the gap sonar. That sounds wild.
Yeah, the gap sonar is, well, it's pretty surprising. They define a specific measurement based on this wobble. They call it geo-ohms. You measure geo-goes at some point no nollar in the number line. And this purely geometric number achieves a Pearson correlation of about 0.74 with the size of the next prime gap, the gap right after n.
Wait, hold on. A 0.74 correlation in number theory, that's huge. That's like 14 standard deviations above random noise, isn't it?
It is. It's statistically massive.
So this simple geometric wobble is somehow predicting whether the very next prime is going to be close by or far away before we even find it.
That's what the data suggests. It's like the geometry is hearing the tension in the number line, predicting whether primes are about to bunch up or spread out more than usual. The local density fluctuation isn't random noise, it's foreshadowed in the wobble.
Okay, that raises a huge question then. If this geometric measurement is so powerful, why all the emphasis in the sources on needing to ground it? Why does the geometry apparently drift if you go far enough out?
Right, because standard Euclidean distance, good old tree dollars equals A2 plus B22, it's fundamentally sign blind.
Sign blind, meaning?
It treats +1 and -1 exactly the same way. Distance is just distance. But the sources argue that number creation, or maybe think of it as number assembly, requires a kind of balance. Their axiom is no +1 without -1 and 00. Creation needs that symmetry.
So a sign-blind measurement messes things up because it ignores this fundamental balance.
Yeah.
Where does the error show up geometrically?
It shows up most dramatically along the diagonals if you map numbers onto a grid, like the Ulam spiral people might have seen. The standard Euclidean distance just gets way too large along those diagonals. It drifts because it assumes space is perfectly flat, but the number space structured by primes isn't truly flat.
Okay, so to fix the drift, they propose replacing the flat radius with this, geodesic chiral metric. And the crucial part seems to be the formula. Chola $2 equals A2 plus B2 minus 22 Ballards. Why the minus sign? What does that do?
The minus sign is where the chirality, the handedness, comes in. Think of it like this. The flat measurement stretches things out too much along the diagonals. That minus term acts like a tension wire. It reduces the effective distance precisely where the old measurement was unstable.
Ah, so it sort of pulls things back into line.
Exactly. It introduces the necessary asymmetry, the handedness. By shrinking the diagonal distance just a bit, this negative chirality grounds the measurement. It forces the geometric wave you measure to align properly with the deep spectral frequencies that RH predicts.
And they explicitly say using the plus branch, making the distance even longer, ruins the fit.
Dramatically worse, yes. The structure demands this specific asymmetry. It needs what they call the odd law to balance the even law.
Okay, explain that. Even law, odd law.
Think of it this way. Analytic RH, like Hardy's ZT function, focuses on the even law, the main symmetric lawful distribution of primes, the big picture rhythm. But this geometric approach insists you must account for the dual component, the odd law, the chirality, the handedness, the residue. You need both channels, the even RH spectrum and the odd chiral residue, to get a stable, grounded, measurable signal. You need both to see the full wave.
Got it. So we have this grounded measurement now. How do we actually visualize the signal it produces? The sources talk about mapping numbers onto the Ulam spiral again, that square grid pattern where primes seem to line up on diagonals.
Right. You use this chiral metric to calculate a kind of average density around rings on that spiral. Then you take the second difference of that density data. For the listener, that's basically just measuring the change in curvature, how much the prime density is bending locally. And what pops out is what they call the geodesic Lune wave, WR. It's this clean, signed oscillation. It breathes around zero, indicating where prime density is momentarily higher or lower than average, according to this grounded geometry.
And the really stunning finding here is that this geometric wave, WRR, is directly correlated with twin primes.
That's right. We know most primes fall into two main channels, modulo 6, like 6K plus 1 and self, and 6K 1, 101. Twin primes, pairs like 17 and 19, are the bridges between these channels.
Okay.
What the geometry reveals is that the structure of the number line, when measured this way, seems to require these twin pairs to form the crests of this WR wave. The fact that this grounded wave doesn't seem to fade out, that it persists as you go to larger numbers, well, it provides geometric backing for the twin prime conjecture.
So the wave needs the twins.
The wave's persistence suggests the structural crease rate needed for twins doesn't decay. Infinite folds, infinite twin pairs, it shifts it from just arithmetic counting to a geometric necessity, potentially.
This whole thing also suggests a different way to think about numbers being built, right? Something about first past the post-assembly time. How does that relate to being prime or composite?
Think of it like building with Legos, but with time constraints. A prime number is one that's structurally irreducible. You can't build it faster by combining smaller blocks. Take the number 4. You can make it with 4 one-blocks, sure. But it's much faster in this model to combine two blocks. So $T2 plus T2 beats $4 times T1. The two 2's slam into place first, making 4 composite.
Okay, so composites have faster assembly pathways using smaller components. What about a prime like 7?
7 is a prime crest. The geometry and this assembly cost idea dictate that 7 resists any faster composite channel. There is no combination of smaller blocks that assembles faster than just building it up, essentially block by block, ending with that final step. That irreducibility is what makes it prime, according to this model. The geometry sets the rules for these assembly races.
All right, let's shift gears slightly. This isn't just abstract theory. The sources claim real-world security implications, specifically for RSA cryptography. How? RSA relies on finding big, unpredictable primes.
Exactly. And this geometric structure, they argue, exposes a subtle but measurable erosion of RSA's safety margin if you use naive prime generation methods.
Naive methods, like just random search.
Like just picking random large odd numbers and testing them. RSA is secure, let's be clear. But its security partly relies on the assumption that finding large primes is uniformly hard, that any large number is as good a candidate as any other. This research suggests that's not quite true, There are structural biases. If you search randomly, you waste time checking numbers in predictable composite corridors identified by this geometric wave.
And that wasted effort translates to a real security loss. They put a number on it.
They quantify it as potentially a 9 to 11-bit shortfall in the effective search entropy for a typical 4096-bit RSA modulus. It doesn't break RSA, not at all, but it means the pool of good primes might be slightly smaller or easier to find than assumed if you know where to look.
And you don't need quantum computers for this.
No, that's the point. This requires only classical computation, using the geometric insights to guide the search more efficiently. The math itself provides the edge.
How does that work? They mentioned phase collapse inversion, PCI, using that wave WR we talked about. How do you invert a wave to find primes?
You look for the collapses, the deepest troughs in that geometric wave WRR. These troughs, according to the model, predict windows where composite numbers are strongly favored geometrically, where they lock in early.
So the geometry points to the cold spots for primes.
Essentially, yes. It tells you where not to waste your time looking. PCI then combines this geometric guidance with standard fast arithmetic tools like the Chinese remainder theorem, or CRT, applied to small number wheels.
CRT helps quickly rule out numbers divisible by small primes, right?
Exactly. So you use the geometry, PCI, to identify the large-scale regions likely to be composite-rich, the troughs, and you use CRT to quickly filter out numbers with small factors within the remaining regions, the crests. It narrows the search down dramatically, focusing effort on these thin, loud corridors where primes are geometrically favored.
So the big takeaway for security is that prime generation isn't perfectly random. It has a structural bias, and this geometry gives a way to potentially exploit that bias to speed up the search.
That's the core implication, yes.
Wow. Okay, what an incredible journey we've taken here. We started with spinning prime vectors, creating a wobble. Then we had to ground the whole measurement using this negative distance correction, this chirality, to enforce kind of creation symmetry.
Right, the odd law.
We tuned this prime wave, WR, on the Ulam spiral grid, and discovered that this same wave seems to predict both the rhythm of twin primes and measurable weaknesses in how we search for large primes for crypto.
It really ties together beautifully. The core lesson, I think, is about symmetry and completeness. Riemann's work brilliantly describes the even law, that lawful, symmetric spectrum of the prime wave. But these sources argue forcefully that you need the odd law, the chirality, the handedness, to actually ground that wave geometrically, make it stable, and measure its practical effects. It gives us a usable, predictive tool that the even law alone perhaps doesn't.
So if the Riemann hypothesis is true, it means this prime wave stays neatly contained within a specific boundary, right? It doesn't wobble too wildly.
Correct.
But here's the final thought I want to leave you with. If this geometry, grounded by chirality, dictates the wave's structure and rhythm, and if that wave demonstrably persists and seems to require the twin prime structure for its crests, does this imply that the infinity of twin primes might actually be a geometric certainty? Something baked into the structure of the number line itself, rather than just an arithmetic conjecture we haven't managed to prove yet.
That's certainly the provocative question this line of reasoning leads to, isn't it? A geometric imperative for twin primes. Fascinating.